Hi folks, this is a video that I uploaded earlier on and it disappeared off the Studio Exchange, so I'm redoing it. In your Copeland text on page 140, Mr. Copeland discusses control technology, in particular motor speed controlling, and he talks about pulse width modulation. And there's not a great deal of detail in the textbook about the particular topic, so it needs a little bit of fleshing out so that it can be understood. So hopefully by the end of this we'll have an understanding of how you can control motor speed with pulse width modulation. So once upon a time in the old days, if you wanted to control a DC motor, AC motors were very hard to control because we didn't have the solid state electronics, silicon controlled rectifiers, the type of electronics and high voltage transistors, that sort of thing. So they would use an analog system to control. So simplest way of explaining it is if we draw a battery symbol, and that's a battery symbol there, we could have what's known as a rheostat or a variable resistor. So a rheostat or a variable resistor, and that would be the way that we control our DC motor speed. So if we had a motor here, a DC motor, and we had say 50 volts across here on the battery, if I took a meter and I measured from here to here, I would be measuring 50 volts. And we've done the idea of a voltage drop across a resistor. So the voltage drop across that entire resistor or rheostat is 50 volts. As we slide this terminal down for this motor, if it was joined at the top here like this, well, we know there's 50 volts across there, so there's 50 volts across the motor. But as we slide our slider down, we get less and less voltage. So if we go to the halfway point, okay, if we were to measure what's appearing at the motor, we're halfway down. Okay, we've divided that resistor in half. So we would end up with a voltage of 25 volts across the motor. And the other 25 volts would be across the other half of the resistor, because 25 plus 25 is equal to 50. So the motor would be receiving half of the voltage. So if this was a light bulb, it would be half as dim. That's a great way of controlling speed in analog fashion, which means in a continuous fashion. But the trouble with that type of control is that you're losing a lot of power across that rheostat. Okay, the only way you can slow the motor down is by wasting power. So it gets very, very hot, and you're going to need a lot of cooling, you're going to need a lot of ventilation, you're going to waste a lot of energy. So it's not an ideal way of controlling speed on a motor. So that's where our idea of pulse width modulation comes in. So that's our analog system for controlling motor speed. Let's talk about pulse width modulation. So pulse width modulation, it's also known as PWM. Okay, that's the acronym for it. So do we know what a pulse is? We all have a pulse, hopefully, if we're alive. Okay, so anything that pulses is doing that. Okay, electrocardiogram, that's your pulse. Okay, width is obviously how wide something is. Okay, so it's how wide our pulse is. Okay, modulation is changing something. So if I modulate my voice, I speak softly and then I speak loudly. That's a type of modulation. If I go from soft to loud, soft again, that's modulating my voice. We'll be talking about modulation in telecommunications a lot when we talk about transmission. We'll have a carrier wave, which is a radio frequency that's being generated, and then we can modulate its amplitude. That's called amplitude modulation, AM, which is what you listen to on your radio. Or we can change the frequency, okay, lots of cycles per second, and then we make the wavelengths longer and shorter, and longer and shorter. So we're modulating the frequency. That's frequency modulation, which you also have in your car radio if you're listening to FM. But for this, we're talking about pulse width modulation. Okay, so there's a thing called duty cycle. So if I had our motor that we were talking about previously, it was a 50-volt motor, and we have our time here and our voltage here, and we just turn on the 50 volts, the motor's running at full speed. Okay, now if I was to, over that time, say at the halfway point, I'm going to turn it off, and then after that turn it back on again, and then turn it off, that is really a form of pulse width modulation, because we're going from there and stepping down. Okay, so we've got pulses happening, but it wouldn't be a very good way of controlling speed, because we turn it on and go to full speed, and get up to full speed, then we turn it off and then start to slow down, and then we turn it back on again and speed up again. Okay, so we want speed regulation to be a little less jerky than that, obviously. So what they do is they create what's known as a duty cycle. So what you would be doing is you would actually turn around and say, if this was a 50% duty cycle, for the time period, we would just turn it off, and turn it on, turn it off, and then turn it on, turn it off, then turn it on, and then turn it off. So that was for that time period that we're looking at initially. Okay, so if you manage to come to a nice compromise for how much it's off and how much it's on, as in the width of the pulses, for the given amount of time, the frequency, in other words, the number of cycles per second of off and on, we would be able to effectively control the speed of the motor without wasting energy. Because when the switch is off, we're not wasting energy. Technically in the electronics, as it's switching off for the very short period of time, which is usually measured in nanoseconds, or switching on, you will have a small amount of power being wasted, but certainly a lot less than with a rheostat or a variable resistor. So this is called what's known as a 50% duty cycle. And what does duty cycle mean? Duty cycle just means for what percentage of time the motor is switched on. Okay, by changing the duty cycle, we can change the speed. Okay, so if we decided we wanted to, and that's a half duty cycle, if we wanted to turn it on for a quarter of the time, what we do is we just make our pulses narrower in width. Okay, so by changing the width of the pulse, we can control the speed. That is pulse width modulation to control a DC motor. Okay, that is what it's about. Now, when we're looking at an AC motor, it's a little bit more complex than that. Okay, so now you'll often see a term when you're looking this up on the internet called VFD. Okay, and that's actually standing for variable frequency drive with pulse width modulation is how it's usually used. So it'll be VFD with pulse width modulation. Okay, that's the way we control an AC motor. Now, if you remember, we went and looked back and we did our revision on our AC motors. DC motors have a commutator, which means you're feeding DC to it. So the amount of voltage you feed will determine the speed. So we just basically change our pulse width in our duty cycle to change the speed of the motor. Now, for an AC motor, you have a squirrel cage rotor, and we have a stator that's being fed with the AC. Now, it could be a three-phase AC motor or a single-phase AC motor, but both of them basically mean that you have a rotating magnetic field, okay? And that induces a magnetic field in our squirrel cage rotor, okay? Which kind of looks like that. And because our magnetic field is going around and around, our rotor chases it, okay? So it's chasing. that rotating magnetic field. But the trouble with an AC motor is the speed of the motor will be determined by the frequency that we supply to the motor. And in the case of mains AC voltage in Australia, we know that we have a 230 volt, and that's RMS, root mean square. That's effective voltage. We talked about that when we did power distribution at 50 hertz, which is 50 cycles a second. Now the motor doesn't spin at 50 hertz. There's a formula for working out revs per minute. Okay. Now how would I work out revs per minute? The formula is equal to frequency multiplied by 60, because it's seconds, multiplied by 2, because we have an up peak and then a down peak. That's why the 2 is there in the formula. And we divide by the number of poles. Okay, which is on our motor we have our squirrel cage rotor in the center, and then around it we have a number of what they call wound stators, okay, which are coils, okay. They're not at the ends, they're around the outside of it, okay, there might be one behind it. So they're around our rotor spinning. We have our poles, okay. Now the number of poles, by dividing by the number of poles, you have you divide by a larger number or a smaller number, you change your RPMs, okay? So for this particular equation here, let's look at a real life example. We'll just get our calculator out. If I had a motor, and for our situation here we've got 230 volts, 50 hertz. If I had a motor that was, say, 4 poles, and we have a frequency of 50 hertz, you might say, well, what's the RPM? Well, we get our frequency and we say 50, we multiply it by 60 seconds, we multiply by 2, and then we divide it by 4, because we said it's a 4-pole motor. And we end up with an RPM for that particular situation of 1500 revolutions per minute. It's spinning pretty fast. Now, if I was to change the number of poles to say 2, we would have 3000. So the less poles we have, the faster it's going to spin. Okay, if we decided to make it an 8-pole motor, okay, we would say 50 by 60 by 2 divided by 8 would be 750 revs per minute. So that's how you change your speed. One way of changing your speed with an AC motor is either construct it with more or less poles or change the frequency. But we can't ring Origin Energy or one of the providers of our power and say, I want more frequency or less frequency. Okay, that's a set thing. We can change the number of poles in a motor, but that's only going to give us still one speed, or we could maybe switch in and out poles, but it'll be a very stepped process of changing speed, and maybe we want a continuous way of changing speed, okay, which looks like an analog system. Okay, so we're going to use this idea of pulse width modulation again, and I'll show you how that works. Okay, so let's just rubber this out, and let's talk about variable frequency drive with pulse width modulation. So what happens is, what we can do is we can change, we've got our input 50 hertz, 230 volts, okay? So this is voltage, 230 volts, 50 hertz, okay, and it's going up and down, and it's going to give us our one speed for our motor for a given number of poles as per the formula, okay? But what we can do is we can chop this signal up. So we chop it up in like a 50% duty cycle. We can change the voltage. Now we already know about that. We did that with it when we were looking at our DC voltage. So that's our input voltage at a given frequency. When we chop it up and we have a 50% duty cycle, we know that we're going to have a lower voltage. So our voltage at motor, at AC motor, will effectively become a smaller amplitude because of that duty cycle, okay? What effect do we have with the voltage? With the voltage for an AC motor, okay, with the DC motor, when you change the voltage, you change the speed, okay? With this particular AC situation, the changing voltage, okay, gives you less torque. So a lower voltage equals less torque, okay? So that's basically less strength on the actual motor. It won't affect the speed. The speed is happening because your rotor is chasing that magnetic field. That magnetic field is not changing its speed, okay? So that is not going to help us in our situation where we want to change the speed, okay? So that's not, you know, helpful for us at all if we just change the duty cycle, okay? But it will give us lower voltage is less torque, and a higher voltage equals more torque, okay? So we've done we've chopped up our frequency that's coming in this case at 50 hertz. How do we change our speed? Okay, we've got a way of changing torque by changing the voltage. How do we change the speed? Well, we know from our equation, okay, what was our equation? We said that it's RPM equals frequency by 60 by 2 over the number of poles, okay? We know that the only thing that can change here, given that the poles is how the motor's built, and these are constants, is the frequency, okay? We have electronics now that allows us to chop up that frequency that's coming in, okay? So we can then say, well, instead of having a 50 hertz cycle coming in, okay, we can play around electronically and chop that input so that it becomes, say, we could change it variably infinitely, but we could like double the frequency, okay? So we then have, for every half cycle, we've got a full cycle, okay? So we've doubled the frequency. So by doing that, we're allowing our RPMs to go up, okay? So there's ways electronically to change the frequency, and that's just why this is called a variable frequency drive, because we can change the frequency, and we can also chop up the voltage that's presented to the motor, and with pulse width modulation to change the voltage. So higher frequency, we're going to have a faster RPM. Lower voltage, we're going to have a lower torque. So if we want to go low torque, low speed, we lower the frequency and we lower the duty cycle. Okay, if we want to speed it up, we increase the duty cycle and we increase the frequency. Okay, so and by increasing the duty cycle, we're going to increase the torque as well. So just remember that duty cycle is going to determine your voltage, which is going to be the torque, and the frequency is what makes the thing go faster or slower for an AC motor. Okay, so DC, we just did pulse width modulation on the voltage, and that's how we controlled our speed. Okay, so hopefully that's helpful. I think it's a fascinating area of electronics and of electrical engineering, it's control technology, and it's come ahead in leaps and bounds from the early days when we had giant transformers because we didn't have any way of switching the mains voltages, and why now your consumer electronics has such tiny transformers because they have what's known as a switch mode supply, and that's what they do. They chop up your 50 hertz and make it a much higher frequency, because if you have a higher frequency, we know according to Faraday's law that you can either make more windings and put the windings on a heavy metal core that's laminated to make a stronger magnetic field. So you get a stronger magnetic field and more windings, or you can make your transformer smaller with a smaller core if you have a higher frequency, because that higher frequency will induce a higher voltage as well. So that's what they do in a switch mode supply. They chop up the mains coming in, and that's why you're able to use a smaller transformer in your more modern electronics. So that is variable frequency drive with pulse width modulation to control speed and torque in an AC motor. And it is also, earlier on we talked about just pulse width modulation for a DC motor. Hope that helps. Watch and do some more research online if you like, but you do now know what pulse width modulation is and how it controls the speed of a motor. See you in the next video.